Hi everyone. So the chapter 1 is crystal structure and let us begin without any wasting any time. So what is a crystal? Crystal is a solid material whose constituents are arranged in an ordered manner at a microscopic level. One way of imagining of what a crystal is, that means if you zoom in, let me take a marker here. If you zoom in onto for example, this is a crystal. If you zoom in to a particular point, what you will find is highly ordered patterns, and these patterns will be repeating after certain distance. So that's how we find that some solid is a crystal or not. And these patterns are made up of things. These things can be atoms, they can be ions. Ions are nothing but charged particles, and they can be molecules like H2O, SiO2, or other things. So, famous example of atoms is silicon. Silicon is used in semiconductor industry. The whole Silicon Valley is named after silicon. So, silicon atoms are arranged in a particular geometry in a silicon wafer from which we use to design microchips on. Ions, I can give you an example of NaCl, which is table salt. It has Na plus ion and Cl minus ion. And here is a picture showing you the model of NaCl. One Na atom is surrounded by Cl, I'm sorry, one Na ion is surrounded by Cl ion on all the sides, and it is packed into a structure like this. And why study crystal structure is an important question. So why to study the structure? I'll tell you why we want to study the structure, because the structure dictates what the property of the crystal is going to be, how it's going to behave under applied electric field. Essentially, uh, electric field is nothing but uh, a voltage, a potential. So, um, things like conductivity depends on the crystal structure. If there are a lot of free electrons, lot of vacancies, the electrons will flow smoothly, hence high conductivity. Conductivity is given by sigma, yes. Resistivity is rho. These are inverse of each other. Oh, that's not important here. And mechanical strength is also defined by the structure. SiO2, diamond is also made up of carbon. Sorry. Diamond is made up of carbon and coal is also made up of carbon. But diamond is the hardest substance on earth. Why? Because it has a certain geometry. It is arranged in a highly ordered pattern. Diamond lattice. It is called diamond lattice, but I'll tell you what a diamond lattice actually is. It's a tetrahedral arrangement of carbon atoms. It is in the later part of this presentation. The color is also defined. So color is defined as in how the light interacts with the solid, how the light passes, what part of the light is getting absorbed, and what the part of the light is getting reflected. So it all depends upon the structure. Here is an example of quartz crystal. The crystal, when applied a voltage across the crystal oscillates back and forth. And we use clever machining to translate that oscillation into the movement of the hour and a minute or the second hand. So, and the SiO2, which I was referring to here, the quartz is made up of SiO2 molecules. Now, SiO2 molecules are also there in glass, but and sand, but they do not behave like quartz crystal. Quartz crystal behaves like this. The exact term is piezoelectric effect because it has a special structure. We will look at the quartz structure also. Maybe not in this video, but I'll give you something about it. So the next slide is why electronic properties are dependent upon the crystal structure. As um, I was telling you why they are depending upon the structure, because um, one way of looking at electrons is in the light of dual nature. That means the electron is a wave and a particle. So a wave, I'm drawing a wave, and A wave will have a wavelength. Now, this wavelength, if it is comparable to this interatomic dimension d, then we are sure that the electrons which are passing through this crystal will interact with the crystal. Um, Crude way of saying it is that the electrons will see what kind of geometry there is. And the exact reason behind it is because there are potential wells when the atoms are arranged in a highly regular manner, and the electrons are sometimes trapped in, or sometimes they come out of these quantum wells. We don't need to go into that much detail. Just remember that if this lambda is comparable to the interatomic spacing, that is d, we know that the electrons will interact, and hence electrons will interact. So the flowing of electrons is current, and current is an electronic property. And if large amount of current flows, that means we know that the conductivity of the material is high, and if low amount of current flows, we know that the resistivity of the crystal is high. And other things also influence, like if there are a lot of vacancies, um, a lot of defects in the crystal, it can also affect the electronic properties. These things are fairly intuitive, and it will be covered in the later part of this lecture series. So how is a crystal formed? It is simple enough. When you add atoms in a constant environment, um, that means there is a lot of less disturbance in this process. If you add disturbance, there will be gaps in this. There will be not a regular arrangement. So let's take an example of a bucket, and you have balls in it, and the balls are of different colors. If you are careful and drop the balls in a sequence, you will get a very good pattern, which is going to be regular. But if you randomly drop the balls, or sometimes forget to drop, or mix it, or drop something else by mistake, drop something else by mistake is like an impurity. Then the crystal structure will not be highly ordered. So in this, we are seeing a lot of different atoms, and the initial nucleation is happening. That means initially they are coming together and sticking together. Some kind of bonding is for bonds are being formed. Then continued growth in the same manner uh, of how it started, and then slowly and steadily this crystal will be formed. The crystal formation is a very slow process. It is not a fast process, and sometimes we see astronauts that go in the International Space Station try to grow crystals there because gravity is less. So the gravity affecting on the atoms will be less, and less disturbance will be there. So the crystal will grow um, in a without defects. So they call it microgravity crystal growing. So you can search it up. It's a thing. And first evidence of periodic arrangement, like who came with this idea that these solids will have periodic arrangement, or we cannot see this arrangement because it is at the level of atom, and we don't have that kind of powerful microscopes back then. We did not have scanning tunneling microscope as we have now. So what we did have was X-rays. In 1912, an X-ray was beamed upon a crystal, and um, of and the I'm sorry, not the reflected, but the coming out of that crystal beams were plotted on a map, and this map was highly regular. A simple way of a simple way of thinking it is that if there is a regular pattern inside the crystal, so the X-rays will be diffracted, which is they are moving away from the initial trajectory in a regular manner. So if this is symmetrical, you see the symmetry here, that means the substance that it is coming out of it must also be symmetrical. That is crystal. So that's how they got the idea. And now they can do many things. Um, Earlier, the experiment was very basic. Now they can rotate the crystal nowadays and map the 360-degree view, the 360 uh, 360 degree in the phi. They can also move in the theta, which is elevation 360 degrees, and then they can move in the radius also. This is spherical coordinates. What I'm saying is they can cover the crystal from all the sides with X-rays and map it all in a three-dimensional array of pattern, and then they can reconstruct like what the crystal structure is possibly inside the crystal, what the structure is. They can do that nowadays. You can look it up. It is crystallography. This field is called X-ray crystallography. So moving forward is some important terms. Now, these terms we will come across these terms uh, in the entire book. So it is important to know what they are. Like lattice. A lattice is a mathematical arrangement of points in three dimension. So we see here there is a space lattice. It is nothing but mathematical points that are mapped in a three-dimensional environment. They can be 3D, they can be 2D. 2D is basically for studying purpose because actual thing exists in 3D, but 2D is helpful uh, in visualizing what shape is at an plane level, at any elemental level. And basis is nothing but the things that we are going to put at these lattice point. Like this can be a basic basis. It can be two ions, like in the case of NaCl, Na plus NCl minus. I am again taking this table salt example. Na plus NCl minus can be a basis. Now, this basis can be mapped onto these each and every point. Now, what will result is a crystal structure. So, you put bases into the lattice point, you get the crystal structure. It is as simple as that. Next, how to define a lattice. So, lattice was nothing but a mathematical arrangement of points. You need vector algebra to do it. So, let me draw a rough figure here. So, this is x, y, and z axis. So, this is x, and this is y, and this is z axis. So to f- to map any point here, like for example, I want to map something on this x-axis. So its coordinate will be going to be 1 comma 0 comma 0, and in vector form it is going to be um, I cap. I think you all are aware about the vector notation, so I will not dive much into it. It is just I cap. So similarly, we can define vectors and we can map this space. So A1 is a vector, A2 is a vector, A3 is a vector, and U1, U2, U3 are integers. So what they are saying is the arrangement is ordered, and if we want to get to any point, we should be able to translate it through integer multiple of these basic vectors. These vectors, like for example, if we want to go to this point, which is simply A1 plus A2 plus A3, we can go there with simple multiplying with simple integers. We can translate this. So this is a general term. It means that with these three basic vectors, we can map the whole lattice. We can map each and every point. Like for example, I want to map like a 1, 7, and 9. So I can map that. This will be something like in A1, it will be only 1 units here. It will be 7 units in this direction, horizontal direction, and in the vertical direction, it will be 9 unit. So what I'm saying is that we can map each and every point. Okay. This might have gotten messy. So tell me if this was messy, so I will explain it again. Um, Here is the thing. So this is a 2D lattice, as we cannot see the third three-dimensional. This is a 2D lattice, and we can see that A1 and A2 vectors are selected. And with these two vectors, each and every point can be mapped. Like if I want to go here, like for example, I want to go at this point. So 1, 2, 3, 4, 5, 6. I can go 6 here, and then I can go into this direction. 1, and 2. So A1 is 6 here and A2 is 2. So A1 comma A2, that is 6 comma 2. So these are going to be the integers, and these are going to be basis vectors to map the whole lattice. And these vectors can be chosen according to our conveniences. Like here, A2 dash is chosen and A1 dash is chosen. So it is at a more shorter angle than this, and this is at an obtuse angle. Obtuse angle is nothing but an angle more than 90. So here the angle is more than 90. Here the angle is more than 90, and here the angle is less than 90, and here the angle is also less than 90 but more than this second case here. And here is like a so it is important to tell you this, that what is a primitive versus what is not a primitive. A primitive is nothing but the smallest possible basis vectors, and the unit cell that is going to be mapped with this vector in 3 dimension. And here I can say a unit square. Unit square will not be ideal to say. I should say unit cell only. Here also unit cell is going to be met. So the primitive is nothing but the smallest volume that is captured by these vectors. So this is not a primitive because it is not the smallest. These three can be considered as primitives because they have a minimum area. Next, so what is a primitive? Here comes the formal definition. So a lattice is primitive if it has the smallest volume and its translation can map the entire lattice. So by its translation, entire crystal can be constructed, which is essentially you want to map each and every lattice point by this primitive. So the vector of such primitive lattices are primitive translation vectors, and the volume is this A1 dot A2 cross A3. This is these are vector, and this is nothing but scalar triple product, which is nothing but something like this. Um, vect determinant determinant of three vectors. This is that. And there is always one lattice point per primitive cell. So the primitive cell will have one lattice point. What it essentially means is this. Let me draw a diagram. I'm not very good at drawing a diagram, but like I'm sorry, I drew a cube here. Now, this is a primitive. It is the smallest thing that is in a lattice. Now, at each and every corner, there is going to be a lattice point. So there are 8 corners in this cube, and this corner will be sharing with the neighboring cells. So the sharing of this is going to be 1, 2, 3, 4, and 4 in the opposite direction. So one lattice point is being shared by 8 neighboring cells. So that means effective volume is 1. So the effective lattice point is 1. So this cube is contributing nothing but only one lattice point. So you can see the lattice point are there. 8 lattice points are actually there, but they are partial. Inside the cell, only 1/8 of each is getting contributed. So effectively, one lattice point is there in a primitive cell. So I'm talking about primitive here. This is important to note that primitive is nothing but the smallest thing that could be mapped in a crystal. So Wigner's site cell is a cell which by default has the lowest volume, and it is always a primitive. And there is a way of making this is you connect every lattice point to other lattice point and uh, intersect Is intersect the right word? I say cut. So you cut it by a perpendicular in exactly the middle, like this. So what you are left with is the Wigner cell, and this cell will by default have the smallest volume. So this is given by the scientist Wigner and Mr. S. I think they are two different person, but I could be wrong. So I should have looked it up. But here we are. I'm recording this in one take. So fundamental types of lattices. Crystal lattices can be carried or mapped onto themselves by translations T and by various other symmetry operations. So let me take a pen and tell you what translations is. Translations are nothing but they are back and forth, up and down, right and left movements. So in all the axes like X, Y, and Z, if we are talking about the coordinate axis, so these are translations and they are integral multiples of it. Like for example, you want to move 2 units here and 3 units up and 5 units back. So these are translations and various other symmetry operations. Symmetry operations are nothing but mirroring. That means if a vector is like this, you put a mirror uh, in this plane, you get the mirror image of it. So this vector. So this is a symmetry operation. Symmetry operations are inverse. Inverse is, for example, if you are in the positive direction, then you get in the negative direction. So these are symmetry operations. Now, this is an important theorem, crystallographic restriction theorem. You can look it up. Um, you can look it up on Google just to wrap your brain around it. I'm gonna be saying this in a very simple way. Here, it's just no gaps rule. That means that if you are taking any kind of structure, like for example, n square, and you repeat it over the entire crystal structure, there should be no gaps. What I mean by that is, like I'm drawing squares here. Are you seeing any gaps in between these squares, like here? No, you're not seeing. And nature wants this arrangement. Nature loves this arrangement. And another example of this is a hexagon. Oh my God, my drawing is very bad. So, but you have seen honeycomb, right? Which honeybees make. They are also in the shape of hexagon. And hexagon also leave no space behind. They can fill up the entire lattice. The crystal structure can be filled up with no gaps. Like here can be other honeycomb. And this kind of structure can repeat itself over the entire geometry of the crystal. So no gaps are there. So hexagons are allowed, squares are allowed, but but pentagon is a tricky thing. If you see here, pentagons are bad, and this is a bad crystal, and this does not exist anywhere in nature. Big red cross. Because if you are seeing this is a pentagon, this is a pentagon, this is a pentagon, but what is this in between? This is a gap. Nature does not like gaps. It has something to do with minimum energy, and the nature wants to be stable and with the least possible energy possible. And something about this arrangement makes the energy go high. So you see the pentagons are there, but there are also gaps, and we do not want any gaps. So yeah, so that's it. That's crystallographic restriction theorem. You can look it up individually. I'm not explaining it in depth because it also confused me very much. I was very much like, oh my God, I had a very bad time wrapping my brain around that theorem. This is an easy way of understanding it, and if it is required in depth later, I'll tackle it in some other chapter. Moving on. Two-dimensional lattices. So, okay. So let me tell you what a Bravis lattice is first. So, Mr. Bravis was a scientist, and he did take a very painful thing and he mapped out what are basic lattices possible in both 2D and more impressively in 3D. So if you see anywhere in the nature, the geometry is going to be one of these only. Here we are talking about two dimension first. It can be a square lattice. Square lattice has 90-degree here in all the four sides. You know what a square is. A1 is equal to A2. The magnitudes are equal, so a square lattice. It can be a hexagonal lattice. And this doesn't look like a hexagon now, but if I draw this, and this, it looks like a hexagon now. So hexagonal lattice is that the both vectors magnitude are equal and the angle between them is 120-degree to map the whole lattice. Rectangular lattice is here. The degree is going to be 90. It is going to be perpendicular, but the vectors are going to be of varying magnitude. They will not be equal. So a rectangular lattice, and the lattice can be of this is a rhombus. It can be of a rhombus. So here the angle is not 90, and A1 and A2 might also not be equal. So that's that. And this is a body centered. Here lattice point is between there, and it will not be called a body center, more like it will be called a rectangular centered it is written here, centered rectangular lattice. Here one lattice point is in between this, and two vectors are there which are not equal, hence a rectangle, and the angle is 90, hence also a rectangle. So these are five types. In 3D it is a little bit um, tricky, but Mr. Bravis made our job easy. He said essentially that in the whole world, find me any crystal, and the crystal's lattice point are going to be following one of these. He made our life simple. So let us see what are there. Just a quick look. So if you're talking about a cube, if the basis lattice is cube, then it can be a cubic. It can be a body-centered cubic, which is nothing but a lattice point in the middle. It can be a face-centered cubic, is nothing but in every face of this cube, at the center, you have a lattice point. So these three are possible. In wait. So here, cubic, I have covered cubic. Let us go with the most interesting one. So most interesting one I find is this triclinic. It is a personal preference, so it's not big of a deal. Triclinic because we can see that none of the angles are matching, alpha, beta, and gamma. None of the sides are matching. So it has full liberty to be of any angle and at any side length, it can be anything. So triclinic is there, monoclinic is there. In monoclinic, only two are possible. You might ask that why only two are possible in monoclinic is because if we try to add something else in monoclinic, it would have resulted in something that we have already counted, like maybe it became a tetragonal. So basically you must think that only 14 types of geometries are possible in when we are talking about 3D. You can look this up. This is a very freely available chart. You can look this up if you want to go into detail. This is not very important right now. What I will say though is this FCC is very important, and this something called hexagonal closed packing. These two are like abundant in nature. Something about this. I'll tell you what exactly. Something about this is nature that the nature prefers. HCP and FCC. Okay, hexagonal is there. We can look at the hexagonal right now. Maybe hexagonal is not shown in this, but later on I have added it in slide, so it's no problem. So again, the cubic, the basic cubic, the body centered cubic, and the face centered cubic. You see a interesting point here. This packing fraction. Packing fraction is nothing but the maximum portion of available volume that can be filled with hard spheres. Hard spheres are nothing but atoms. That means here 74% is filled in FCC. Here only 68% is filled. Here in simple cubic only 52.4% is filled. So nature will obviously prefer. We remember that there was a no gaps rule. So the nature prefers the minimum arrangement, and the minimum arrangement is it does not want any gaps. In FCC we can see right away that The gaps are very less when compared to this. So to maintain this shape, nature will have to expend extra energy, and this will come in natural. Um, so FCC, you can see the some characteristics of these lattices. Uh, yeah, that's pretty much it. So next is index system for crystal planes. One thing I found interesting was nowhere in this book the name Miller indices was mentioned, because in the internet and in other books like Benji Streetman or Donald A. Neiman, which are semiconductor books, this is clearly known as Miller indices. But in this book, no mention of Miller is there. Maybe uh, I don't know. I don't want to think about it. Here, let me show you how a Miller indices are made. You take a coordinate system. You cut the axes of where your plane is lying. Then you take, like for example, it is 3, it is 2, and it is 1 intersecting. The plane that is intersecting these axes. You take it and then you write it down like 3, 2, 1. Then what you do is take their inverse. So 1 by 3, 1 by 2, and 1 by 1. And then you make this fraction into a whole number, like simply by multiplying with 6 it can be done. So 3 twos are 6, and 2 threes are 6, and 1 is going to be 1. So 2 comma 3 comma 1. So it is the Miller indices. Here we can see some simple things. 1 0 0 is Miller indices for this plane. 1 1 0 is for this plane. That means this zeroth thing. There is no cut on this axis, in this on this vertical axis. The plane is only intersecting these two axes in, and it is not intersecting the third axis. Here 1 1 1, each plane, the plane is intersecting the each axis. Here 2 0 0, that means the twice of the x-axis is cut, but y and z are left. This is 1 dash. 1 dash is nothing but minus. That means if this is positive, following the Cartesian rule, then this will be negative. So we can see the back side of the cube is intersected. Next, calculates his Miller indices. Okay, we already calculated the Miller index, but let me calculate it again. This is A1, so we write 3, we write 2, A2 for A2, and then for A3 also we write 2. We do nothing but takes their inverse, and as I did for the previous, make it a whole number, multiply with 6, 6, and 6. So you get 3 twos are 6, and 2 threes are 6, and 2 threes are 6 again. So its Miller index is 2, 3, 3. And if you enclose it in this normal parenthesis, it is a plane. And if you enclose it in this square bracket, it is a vector. And vector is going to be perpendicular to this plane always. This much vector algebra you must know, I think. Even if you don't know, it's no big deal. It will just take 3 days to learn the whole vector algebra. Okay, I don't want to discourage anyone. Simple structures. So this is sodium chloride structure. I was very mad when I found out this is a FCC structure, but since I spend a lot of time on it, let me tell you in a simple way. So sodium chloride is nothing but Na plus NCl minus. Here the crystal is FCC, but what is happening is the lattice is FCC. That means let me draw it and spend some time here because it is worth it. So I'm drawing a cube, and if you see the chlorine is FCC. If you just observe the chlorine, it is FCC, like at all the four corners, in all the center of the faces. You saw it, right? This is an FCC. But Na plus is extra, you must think, which is right. Na plus is extra. So what is actually happening is this FCC is just lattice point. It is just a lattice. That means it is a point. Here we are not thinking about ions. The basic structure is FCC. And to each and every this lattice point, let's take an example of this point. What is getting mapped? Like you would remember the difference between lattice and basis. The basis is Cl like this and Na like this. At approximately it is half, half, half. So this is a three-dimensional position. So if Cl is at 0, 0, 0, then Na is at half, half, half. So like this diagonal shape. If you notice, if you notice this diagonal shape from the for the center Na, this diagonal shape is one basis. Let me uh, let me pour my pen on this. So this, and I will use red also because I want to explain. This is Cl minus and this is Na plus. This one thing which I have colored so brutally is one basis. This is one basis. And if you continue this symmetry throughout the crystal lattice, you will see that at each and every FCC point, one basis is present. So this thing is mapped here, it is mapped here, it is mapped at every lattice point. So that's how it is FCC. If you didn't understand, I'm sorry. As time will go on, my explaining capacities will improve. So, and here is the model of NaCl, how it is, how it looks like. So each Na is the smaller one, is surrounded by chlorine on all the sides. Here we can see it more beautifully. If I had not made a mess of it. But yeah, so moving on, simple structure, salt. This is stable salt. This is FCC. Next, FCC. How it is FCC? Yeah, the same thing that this is an FCC. This is a basis and the lattice is FCC and basis is Cl at 0, 0, 0 and Na at 0, 0.0, 0.5, 0.5. So I explained it there only. So I have included this slide to explain, but I explained it before. So moving on. Cesium chloride structure. Nothing special, same thing. Cl minus ion at half, 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 and cesium ion at 0, 0, 0. But the thing is that it is a body-centered cubic structure lattice, which is filled with bases of this. Nothing more. Hexagonal close packing. Nature loves it. So nature loves two things. Nature loves FCC and nature loves HCP. And interestingly enough, both packing fraction are equal. Here we can see this hexagon at the top. Here we can see hexagon at the top. And here you can see the B layer which has three lattice points. So this is hexagon close packing structure. And these are the elements that exist like helium exists. Oh my God, helium is a gas. They have made helium crystals. At what hell would you find helium crystal, solid helium? Actually, it is at 25 atmospheres, ATM, which is an enormous pressure and at a very cold temperature. So I know this, okay? I searched it up. I looked it up. So you find zinc crystal, which is Zn, you find titanium, and you find this. Is it yttrium? I'm a nuclear scientist, so this might be yttrium. We find this in the spent fuel of okay, beryllium, magnesium, cadmium. Moving on. In this slide, I will be telling you how in nature only you see mostly HCP, which is hexagon closed packing, and FCP or FCC. You see only these two types of arrangement in the majority of cases. Why it is? One reason is like the packing density, 74%, both have 74%. But if you go by normal common man logic, If you have spheres, spheres are nothing but atoms. How will you put it? Like this only, right? How I'm drawing, not how I'm drawing, how in the image it is drawn. You will put it like this, and there are going to be some gaps left. So this is, you take a flat surface and arrange a set of spheres. And then you face an important choice, where you shall keep the second layer. Obviously, you have some choices. You can keep it in the gap, like here, wherever the plus sign is. You can keep the next set of sphere, which I'm drawing with a smaller green color. You can keep the next set of spheres here. Okay. And after that, you will face a choice. The AB is fixed. You keep a set of sphere on the bottom surface, all are A's, and second set is B's. You filled all the gaps. You are very happy with yourself. Okay, I have filled all the gaps. Then you face a choice. If you want to repeat the bottom layer again, or you want to make the gaps between the B and you want to place in between the gaps of the B. So here, let me create a stack. The bottom layer, you kept A. In the gaps, you filled B. Now you face a question mark, a choice. If whether whether you shall put a C here or you should repeat the pattern of A again. A means that the balls that were at the bottom, you want to again arrange it in the A manner, but you want to again fill the gaps and put it in the C. Here it is written, let me read it out the whole thing. Close packed layer of sphere is shown. Sphere because spheres are atoms. Atoms are spherical. Talking field wise, electromagnetic field wise, they are of a spherical shape with centers point marked at A. So these are normal arrangement. You cannot change A. A is going to be always there. A second and identical layer of sphere can be placed on top of this, above and parallel to the plane of drawing, with centers marked over the point B. Again, you cannot escape B. B is at the gaps of A. Okay, now this is done. There are two choices for a third layer. Now you face a choice. And in this choice, nature makes its decision of whether giving FCC or whether giving HCP. Actually, I do not know how nature makes this decision. I am very curious to find out. Hopefully, throughout this book, we'll find how we'll be making this. So, uh, the structure is hexagon cross packing. If you again follow the A structure, which is AB, 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 and it is face centered cubic if you follow ABC, ABC, ABC. Okay. Next, diamond structure is important because I'm a semiconductor engineer and all semiconductors mostly occur in this diamond shape. Silicon, germanium, and gallium arsenide. Gallium arsenide is a direct band gap semiconductor. That means it is optical, and when a hole and electron recombines, they give off um, photons. So this is not important here, but this is very important for if you taking the perspective of if you are taking the perspective of semiconductor industry. So here the basic shape is this. We have a tetrahedral. Tetrahedral. Let me draw here. So at each and every atom of silicon is going to be sharing with four other atoms of silicon. So this is the basic structure and it is repeated. The basis here is again one silicon at 0, 0, 0 and one silicon at 0.25, 0.25, 0.25, which is 1/4. And the structure is again FCC. So you have that cube, like I explained it right. So uh, you have this FCC. This is lattice is FCC and basis is two silicon atoms at 0, 0, 0 and at half, half, half. And if you fill this basis in the FCC, you will find something like this repeated all across. I'm sorry, cubic zills. What is happening? Cubic zinc sulfide structure. Cubic zinc sulfide structure also exists in this way, except varying that there are two different elements, zinc and sulfide, and um, it is called zinc blendy. the structure is same, but the elements are too different. Here 000 will be zinc, and at sulfide point, at 1 by 4, 1 by 4, 1 by 4, a sulfide ion will be there. In If you see a semiconductor like silicon is in this arrangement only. And another famous is gallium arsenide. Gallium arsenide is also in this arrangement. Only difference being that here sits a gallium, and here at 1 by 4, 1 by 4, 1 by 4 sits an arsenide. So that's the only difference. Oh, just get this into our mind that this tetrahedral is diamond, and this is important in the semiconductor industry. STM, scanning tunneling microscope. So this is oh my god, this is an amazing thing. Scanning tunneling microscope. Let me tell you what a tunneling is. So if there is a wall is h height, and you are a person of height x, then you can never cross this wall in classical physics speaking. But if you are a quantum mechanics man, there is a probability that you will cross this wall. There is a probability then you that you can. It is a non-zero property. It is an exponentially decaying probability, but there is a probability that you will cross this wall. So here the probability is that you are crossing these points, right? One, two, three. So here probability, because there is no wall, you can easily cross here these points. So probability is one here. And if there are states here, there are possible situations here. Like for example, here you're getting what I mean to say, right? If they are possible, if you are seeing the length of which points you are crossing, here the probability is one because there is no barrier. Here there is a barrier at 2 points. So at this barrier, the probability drastically decreases. That means something that can seem impossible is also possible in quantum mechanics. So how this works? Let me explain you very simply. This is a piezoelectric device. That means piezoelectricity is nothing but it translates stress into voltage. So if the tip is put down and it interacts with the lattice atoms, then there will be tunneling and this circuit will get complete. You will find a current pulse. This pulse will be mapped in over the entire lattice. So you will find this kind of shape, and this shape is by movement of this tip back and forth. And when this tip touches, the electrons get to tunnel. They tunnel and then they complete the circuit via this battery, and you map it and you get some structure like this. And using advanced signal processing, you can map the entire lattice, and you can get a picture of it. What you are essentially getting is the picture of fields. You're not getting a physical picture, but us humans like to look at something to understand it. So yeah, that's that. Random stacking and polytypism. I have explained this diagram in the, this is not a diagram, this is a figure in a previous slide, but I will tell you again this. So if you have spheres are nothing but atoms. There is only one way of arranging the bottommost layer, which is A. Then you can fill in the gaps in uh, with other spheres, which is B, and then you have a choice whether to go with C or whether to continue with A. Okay, so this is basically, and depending upon this choice, you get the FCC or you get a HCP. So this is the basic gist of this diagram. Now random stacking is there. So that means there is no order. It is completely random. Like we can see A, B, C, A, B, A, C, B, C. So there is random order. And this occurs in nature. Yes, it occurs in nature. And faults during crystal growth, low stacking fault energy, rapid cooling, deformation. If this careless crystallization takes place, then random stacking can occur. And what is polytypism? Polytypism is that it must seem random at first, but a set of pattern will be repeating after certain distance. So you are saying A, B, C, A, C, B, and this itself is going to be repeating. So we have silicon carbide. Silicon carbide is in a semiconductor language, silicon carbide is a high band gap, wide band gap semiconductor, and it is used um, as a substrate sometimes in if I'm not wrong, in semiconductors. And it has 100 plus polytypes. That means like these letters are arranged, it has 100 plus. In 3C SiC, it is ABC, ABC, ABC. In 4H SiC, it is ABAC, then again ABAC, then again ABAC. And in 6 SiC is ABC, ACB, and this thing will repeat itself. All are SiC, but properties differ because of their shape. This is very interesting and you must look it up. And maybe in the further chapters, we'll get to expand on this. This is just an introductory chapter. So I have finished it. It was a very painstaking process, and I have never taught online. I've never taught offline also. So, and this is some kind of personal achievement. So, thank you for if you are here till the end, and good night. It's night here. So good night. Bye. Like and subscribe if you can. Thank you.